So this is our first lesson in Unit 910, rates of change, limits, and derivatives, and we're going to start with rates of change. So by the end of this lesson, you should know how to find the average rate of change from a function, how to use average rate of change to estimate the instantaneous rate of change, and we're going to spend some time talking about the difference between average rate of change and instantaneous rate of change. And then we're going to think about how we interpret average and instantaneous rates of change and make a connection to the graphs of our functions. So you've done a lot of this stuff in advanced functions. You've also seen this a bunch of times in physics probably. So we'll just sort of refresh your memory here on what's going on. So here we've got a situation. A rock falls from the top of an 80-meter cliff. After t seconds, it is s meters above the ground, where s as a function of t is 80 minus 5t squared. So we've got a function here that tells us the position above the ground, okay, as a function of t. And we're going to be asked to do a couple of things here. Number A here, find the height of the rock after 1 second. Okay. Now, this is a pretty easy application of functions. We are given a value for the time here. We've got a function that tells us the height as a function of time. So we just need to sub that time value into our function. So what we want to evaluate is s at that value of time, 1. So s at 1. And that's going to be 80 minus 5 times 1 squared. And we can just evaluate this, plug it into our calculator to get 75 meters. Part B asks us to find the average velocity of the rock between t equals 1 and t equals 3. So velocity is our first example of a rate of change. Velocity is the rate of change of position with respect to time, or as they express it in physics, we would say that velocity is equal to displacement divided by time. So to answer this question, we want to figure out how far this rock has moved, so it's displacement, and the length of time over which it has taken to move that particular distance. So mathematically, we want the change in position, so delta s, over the change in time, delta t. And we're going to call this the average velocity. I'll use AVG for average velocity because it's done over an interval of time, okay, between two time periods. Okay, so we want the average rate of change, or the average velocity, over this interval from t equals 1 to t equals 3. So if we want the change of position up there in the numerator, we want to find the position at our 2 times. Well, the position at our 2 times is just given by our function. So we want to evaluate this function, s, at time 3, and we want to subtract the position at time 1. So that's going to be our change in position, the position at time 3 minus the position at time 1. And for our change in time, well, we want to go from our second time value is 3 seconds. We're going to subtract our initial time value of 1 second to get the change in time here. So let's see, we already know what our position was at 1 second. That was 75 meters. Off to the side here, we can figure out what our position was at a time of 3 seconds just by plugging 3 into that position function, and that would get us 35 meters. So our average rate of change is going to be, there's a bit more space here, 35 meters minus our 75 meters divided by 2. 3 minus 1 is 2, which is going to be negative 40 over 2, or negative 20. And our units here, because our positions were in meters and our times are in seconds, is meters per second. So there is our average velocity, change in position divided by change in time. Now, this is negative. Is that okay? Liam's shaking his head. He says no. You're shaking your head yes. What do we think? Good? Bad? What is that negative sign telling us? It's going down. It's heading down towards the ground. Okay? Our function is measuring the number of meters above the ground. So if the number of meters above the ground is getting smaller, our rate of change is going to be negative. So this just tells us that it is moving towards the ground. Or another way of saying this is that S is decreasing. So you might have been concerned there for a little bit that velocity is a vector and that I didn't have any direction information in here. Well, we do have the direction information. It's either a positive direction or a negative direction. So that's our average rate of change. What if we want the instantaneous rate of change? Okay. Or the instantaneous velocity at t equals 1. So notice the difference in language here. We had an average rate of change over some interval or between two values of time, whereas we have an instantaneous velocity at a very particular point in time. So we want to know at t equals exactly 1 second, how fast is that rock falling at that instant, okay, or the instantaneous rate of change. And you did this kind of question in advanced functions. And what you did was you found the average rate of change using that method that we just used on the last page. Our function evaluated at time 2 minus our function evaluated at time 1 all over t2 minus t1. And then you took one of your t values, okay, this t2, and you said, let's make our t2 values closer and closer to our t1 values. So t1 here is going to be our t equals 1. Call that t1. Okay. For 1 second. Okay. t1 is the time at which we want to find this instantaneous velocity. So we pick a second time that is some interval away from t1. We find the average rate of change, and then we make t2 closer and closer and closer to t2, calculate the average rate of change each time, and we look for sort of what kind of a trend we have in these average velocity values. So a way of sort of writing this is that we are taking t2 and we're letting it tend toward t1. Okay, the arrow there just kind of means tends toward. Okay? Or this time interval, delta t, between our two values of t, is tending towards 0, making it smaller and smaller and smaller. And we do this, we look for a trend. Okay? And this is where the tables came in. Because one way of looking for a trend in these values of the average rate of change was to set up a table. Okay? So we've got a column for t1, a column for t2, a column for our change in t, a delta t, our values for position at each of these t1 and t2 values, and then the final column is our average rate of change over the interval from that specific t1 value to that specific t2 value. And this is where we are looking for the trend in that final column there. So let's start filling this in. T1 is going to be 1 no matter what we do. That's the point where we want to find the instantaneous rate of change, or the instantaneous velocity. For our T2 values, we are going to start a small distance in time away. So I'm going to choose 1.1. Okay? And we're going to gradually change our T2 values so they get closer and closer to our T1 value. So if I start at 1.1, my next one might be 1.01, then 1.001, okay? And I could go on and on and on and on. So our change in time is going to be start at 0.01, then go to 0.001, sorry, 0.01 and then 0.001. So delta t is getting closer and closer to 0. That interval between our two times is getting smaller and smaller. Our position at time 1 isn't going to change. We've already worked this out. It's 75. What is going to change is our position at time 2, because we're changing the value for t2 each row of this table. So it's going to go from 73.95 to 74.8995 to 74.9899. And then we can take our delta t, our s, our position at time 2, our position at time 1, and calculate our average rate of change. We get negative 10.5, negative 10.05, negative 10.005. Now, that's just straight calculation, okay? This is where the important part comes in. What is the value that our average rates of change, that final column there, appear to be tending towards? Okay, if we were to keep going on this table, making delta t smaller and smaller and smaller and smaller, what would we end up with? Like, where's all of this going here? Shane? Yeah, it looks like everything's heading towards negative 10 here. So that is our estimate for the instantaneous rate of change. Okay. So we don't just pick one of these numbers from that last row, that last column there, okay? Because none of the values that appear in that last column are actually correct. None of them are the instantaneous rate of change. What we're looking for is, if we were to keep going closer and closer and closer, what would we eventually end up with, maybe? Okay. Now, for confirmation, you were sometimes asked to do this, this table twice, okay? When I did it the first time, I picked T2 values that were larger than my T1 values. I'm still interested in finding the instantaneous rate of change at T1, but now I'm going to choose T2 values that are smaller than T1. Okay? 0.9, 0.99, 0.999. Okay, so we're still making T2 closer and closer and closer to T1, but we're doing this from values of time that are less than our value of T1. So our delta T values here are all going to be negative. And we can go ahead and we can calculate all of this stuff. Okay, and so on and so on and so on. So when we go ahead and we work out our positions at time 2, we'll get things like, let's fix that. There we go. 75.95, 75.0995, okay, 75.0099, and so on and so on. So when we work out our average rates of change, I get negative 9.5, negative 9.95, and then negative 9.995. So we ask ourselves again, what is our estimate from this table for our instantaneous rate of change at t equals 1? Well, what are all of these values tending towards? Negative 10 again. So again, V instantaneous is equal to negative 10 meters per second. So this is our estimate of our instantaneous velocity. And we want them to be the same, whether we approach from smaller values of t or we approach from larger values of t, because this is sort of telling us that we're doing all this whole thing correctly. So when we approach from larger values of t, it's sometimes said that we are approaching t equals 1 from the right. O-A-C-H-I-N-G, approaching from the right. All right, so from larger values of t, down here we are approaching from the left. We're approaching t equals 1 from values of t that are smaller. Okay. So this estimate for our instantaneous value of t is sometimes called the limiting value. Okay? This is the value that each of our individual approximations from our average rate of change are tending towards. So what we are actually doing in these tables is we are taking a limit. Okay? And we're going to talk more on Wednesday about what limits actually are and what they mean. But this is just a convoluted way of taking a limit. Okay? So we're good on this. You've seen these tables before, right? Okay. What does this mean graphically? Okay. Well, when we were trying to find the average rate of change, we were going between two different points. Okay, we were going from T1 to T2. So we had 2 points on our graph that we were looking at. We had a point here, and we had a point here. And one point was T1 S1. Okay, so our first time and our first position. The other one was T2 S2. And what we did was what we calculated was the change in position over the change in time. S2 minus S1 over T2 minus T1. When we do that calculation, change in S over change in T, or change in Y over change in X, what are we calculating? Well, it's like we took a line, connected these 2 points on our graph, and then calculated the slope of that line. Now this line connecting 2 points on our graph is called a secant. So the average rate of change is the slope of the secant between the 2 points. So this is very similar to calculating the slope for a linear function that you did back in grade 9. Now, what about when we were doing instantaneous rate of change, where we were looking at this single value, T1? So we only had 1 point that we were really interested in, and what we wanted to do was find the instantaneous rate of change at that particular point. We can think of this graphically as, if a secant line touches our curve at 2 points, here we want a line that only touches our curve at exactly 1 point. Okay? Because we're interested in just this point, T1. So you can think of it as this curve is coming along, and we hit T1. What direction is this curve going at that point, T1? If we were to stop sort of curving and just go straight, what direction would that follow? So a straight line that touches a curve at exactly 1 point is called a tangent line. So our instantaneous rate of change is the slope of this tangent. how did we get the slope of that tangent? Well, we took a secant line, like this one here, and we had two endpoints, and we took one of the endpoints, put it right on T1, and then we took the other endpoint some distance away, and we sort of moved it closer and closer and closer. And as we moved it closer, the slope of that secant line became closer and closer to the slope of the tangent line that we're actually interested in. So we found this slope of the tangent by finding the limiting value of the slopes of our secants, the series of secant lines, as we took T2 and we moved it closer and closer to T1. So the limiting value of the slopes of all of our secant lines as we made T2 closer and closer to T1. Mathematically, we can write this as a limit. So this LIM just means the limit, or find the limiting value, or find the value that all of these things are tending towards, as T2 tends to T1. And what are we trying to find the limit of? Well, the slope of the secant, which was S2 minus S1 over T2 minus T1. So this is the expression that we're going to use going forward to find the slope of a tangent. Okay? Or we can think of it as the limit as that difference, delta t, gets smaller and smaller of delta s over delta t. So just a mathematical way of summarizing that process we were following. Finding the slope of the tangent at various steps, moving one end of the slope of the secant at various stages, moving one end of that secant closer and closer and closer to the point that we were interested in.